Continuing our logic from class, we were discussing this notion that it is a useful thing to be able to know the angle between two vectors. And we described a whole host of physics situations in which it was a good thing to know that. So let's say I have a coordinate space. It's a Cartesian coordinate space. And I've got a vector A, and I've got a vector B. A little different than the A and B that I drew before. So A would be so many positive I hat plus so many positive J hat, and B would be so many negative I hat and then so many positive J hat. And what I'm doing here is I'm looking for the angle between these, theta AB. Right? We talked about the situation of comparing velocity versus acceleration vectors, if these were two force vectors, that might be useful to know. Or in the concept of work, we described the angle between the force causing the change and the displacement, which is evidence of the change, and the work equation that comes from those two variables. So we had a whole host of those situations. But what we're just showing from a generic abstract notion here is that I can find that angle by just using coordinate geometry, because if I know those two, as well as the vector that goes either from B to A or A to B, let's say the one that goes from A to B, doesn't matter, because the one that goes from A to B is going to have the same magnitude as the one that goes from B to A, you can see that doing A and then doing this vector gives you B. So A plus this vector gives you B, so I've drawn the vector B minus A then. Okay? Right? Now, if I had drawn it from here to here, it'd be the vector B plus the vector whatever gives you the vector A, and that would be the vector A minus B, but the magnitude of A minus B is equal to the magnitude of B minus A. So let's just define our terms there, right? So I can then now use the law of cosines to show what's going on between these. But before I do that, I want to just bring out this notion that this geometry is true not just in 2 dimensions, but in 3 as well. When we have any two spatial vectors, right? These could be described in terms of an I, J, and a K, right? All of these. Now notice that no matter what sort of actual directions these go off in, these vectors would form a triangle as well. Let's say if this is vector A and this is vector B, if this is A and this is B, then this vector here would be B minus A as well. And it doesn't matter the orientation of those. In fact, it's sort of interesting that any two non-collinear vectors can be said to describe an area in a plane. Now that plane might not be the XY plane, might not be the XZ, ZX. It might be some sort of weird alternate plane that would have an equation of some constant A plus some constant B plus some constant C, Z, excuse me, equals C, right? Because we know that that's the equation of a plane. But we know that those two non-collinear vectors would be able to describe an area. What would that area be? I'll just draw that out. That would actually be the area of a parallelogram described by drawing the vectors like this, okay? Where you would draw A, then B, B, then A, and I get this parallelogram. But more about that parallelogram later. Notice I said two non-collinear, because if A and B were along the same span, along the same direction, that would just mean that there would be no area involved there, and not exactly what we're talking about. But we'll come back to that notion. So what I'm about to describe, even though I've drawn it in 2 dimensions, it doesn't have to be 2 dimensions. So let's define our terms then. We know vector A is AX I hat plus AY J hat plus AZ K hat. Remember, I'm abstracting this from this picture. This picture is just helpful in terms of being able to see what I have there. And then B, vector B, is BX I hat plus BY J hat plus BZ K hat, okay? And that would mean that vector B minus A is just simply bx minus ax I hat plus by minus ay j hat plus bz minus az k hat. Okay, so those are the terms. Now, as we've seen here, these three, ba and b minus a, form a triangle of some description. It doesn't matter what type of triangle that is, but I know I can use the law of cosines. So remember what the law of cosines says. That says if I have two vectors, or I have two sides, and the side opposite an angle, that I can do this squared is equal to this squared plus this squared minus 2 times this times this times the cosine of this angle. So what does that look like for us? Well, that means the magnitude of b minus a, doesn't matter what its direction is, right? Just how long it is, because now I'm just dealing with a triangle. Squared is equal to the magnitude of a squared plus the magnitude of b squared minus the magnitude of a, or 2 times the magnitude of a, the magnitude of b, cosine of theta a b. Okay, that's what we've got there. So what are we going to do here? Well, we're going to do some substitutions of some of these things to see if we can come up with anything interesting. Okay, so what do I know? Well, I know that I can find this magnitude and square it, right? If I find this magnitude, that would be the square root of the sum of the squareds here, and my unit vectors would go away because that would just be the x component squared plus the y component squared plus the z component squared. So, and then because this is squared, that square root would go away. So what I would have there is bx minus ax quantity squared plus by minus ay quantity squared plus bz minus az quantity squared. Okay? Now, notice there, very clearly, the unit vectors go away because that's what the operation of doing the magnitude does. It strips out direction. Over here, let's say that I do kind of something similar. I've got magnitude of a. So that would be the sum of the square roots of the magnitudes of the components. But the square root is going to go away because of the square. So I'm left with ax squared plus ay squared plus az squared plus bx squared plus by squared plus bz squared minus, and for my own purposes, I'm going to leave this in this format simply because, simply because. I know what the result is going to be, and so I'm just going to tell you that expanding this out is not going to be useful for what we're doing. But we will expand out this side here. So I've got a square there. This is going to get kind of messy, so or long, so I'm just going to be very cautious with this. I'm going to get bx squared and then minus 2bxax, right? Plus ax squared. Now, this step here, rather than try and like go all the way across, I'm just going to go plus, and I'm going to indent here by squared minus 2 byay plus ay squared plus, and then indent again, excuse me, bz squared minus 2 bz az plus az squared, and all of that is equal to this, right? Now, hopefully what you're seeing is the canceling shall begin, right? There's a huge cancel fest going on because I've got some of the same terms on both sides of the equation, right? You'll notice here that I have a bx squared and a bx squared, an ax squared and an ax squared, a by squared, a by squared, an ay squared and an ay squared, a bz squared and a bz squared, an az squared and an az squared. Okay, it's a lot of canceling, so I'm just going to write what I have left then, and maybe we can see some more things to do. I've got negative, and you know what, I got bx, ax, those are multiplied together, so I'm just going to, oh, hold on, you'll also notice I have a negative 2 in each term. That's interesting. So I'm going to factor out the -2, and I know this is bx, ax, but that's the same thing as ax, bx, right? I can just flip the order of that because those are just coefficients, right? There's nothing magical about that. Okay, and then that's going to equal, all that's gone is -2 a b, magnitude of a, magnitude of b, cosine of theta AB. Oh, well, looking at that, that's super interesting because that factor of -2 also disappears, and I'm left with then a really curious expression. And that curious expression is that ax bx plus ay by plus az bz is equal to the magnitude of vector A times the magnitude of vector B times the cosine of theta AB. And that's super interesting as a result. So what we're going to do is we're going to talk about what the meaning of this is, define a new operation that takes this as its meaning, and then kind of move on from there, right? But the promise that I made was that I would have a very easy way of finding the angle between two vectors. So let's just use this equality then to do that. And we'll do it nice and simple with two vectors in 2 dimensions. So let's say vector A is equal to, I hat plus 4j hat, and then vector B is equal to -3i hat plus 2j hat. I'm just making things up, right? So let's see how I could use and find the angle between those two vectors. So let me just quickly sketch it. Not that we need to do that, but this is 1 to the right and 4 up, and this is 1, 2, 3 to the right and 2 up. So I'm looking for that angle there. So I just draw that so that when we get an answer, we can kind of sense check it here. All right. Here we go. So this says just to fill in the template here. So I've got AX. Well, actually, notice here, I need the magnitude of A and the magnitude of B. So let me just do some prep work, some mise en place there, right? This is going to be 1 squared plus 4 squared. Remember, the magnitude operation strips out direction, right? And so that's going to be the square root of 17. Now, I'm not going to get a decimal for that because that's not the final answer. If that was the final answer, find the magnitude of A, I would want to know the decimal of that. But because I'm just going to plunk that in there, it's internal work, I'm just going to leave that in terms of square root. And so this is -3 squared plus 2 squared, just taking the coefficients, throwing them in, 9, 4, radical 13. Okay, so now I can just come up here and plunk in everything I have. So this becomes 1, and then the bx is -3, plus the ay, which is 4, the by, which is 2, and plus, and these are both 0 because there is no z component of this. And then this is radical 17, radical 13, cosine of AB. So let's just come over here and see what we have. We have -3 plus 8, so that is going to be 5 equals rad 17, rad 13, cosine of theta AB, and therefore theta is just going to be the arc cosine then of 5 over rad 17 times 13. And so I can just take that, plunk that in my calculator, 17 times 13, square root of quantity, 1 over times 5, you get 0.336, and then the arc cosine of that. Our cosine of that answer, and we get 70 degrees, or 70.3 if we want to be a bit more precise. And if we look at that, that's actually pretty good, because looking at that, I was kind of expecting an acute angle because of the way that I graphed it, so it's nice that the math seems to conform with what I have, okay? So let's look at what it is that we have, this thing that's left, and define some stuff, because that's an equation that's going to be really useful. So what this thing seems to do, if we look specifically on the left side, because we're going to want on the left side and on the right side to talk about kind of a meaning for that. So let's look at the left side of that expression. You'll notice that ax bx plus ay by plus az bz. A couple of things about that. First, and I think most importantly to recognize, that this result is a scalar result. It's just taking the coefficients. The directions have vanished. So it took the coefficients of a vector and turned them into scalars. Interesting. The other thing I hope you think that you see about this is that this seems to multiply together the like parts of a vector, right? The x part of A plus times the x part of B, the y part of A times the y part of B, etc. Now, if you think about it, why would that be related to the angle between the vectors? Well, if the x components of the two vectors are, different signs, right? They kind of point in different directions. That's going to suggest a larger angle between them. Same thing if the y components are in different directions. So like if I had a vector here, and that was vector A, and a vector here, that was vector B, one in the first quadrant and one in the fourth quadrant, notice that this product here would come out to be a negative number, and I would get this massively acute angle, right? But similarly, if the two vectors kind of lay along the same sort of direction, right here in the xy plane, these would have both positive i's and positive j terms, and then this product would come out to be positive, okay? And so with that, we can see that sort of like the more that the vectors go in the same direction, the more likely this thing is going to be positive, and the more they go in opposite directions, that the more that this is going to come out negative. So if the vectors point similarly, this thing comes out positive, the result of this process comes out positive, and if the vectors point oppositely, this thing comes out negative. All right, super interesting. So I guess the question is, well, what happens when this thing comes out 0? Well, let's look at this specific example of a two-dimensional vector if this comes out 0, right? So that would be ax bx plus ay by equals 0. We won't worry about the c terms just to make a point here. So if you notice here, I can subtract ax bx is equal to negative ay by, ax ay is equal to negative by over bx. So if you think about this, ax over ay, by over bx, or ay over ax equals negative bx over by. Well, that should be kind of familiar, actually. So if I have a vector A, you can kind of think of the ratio of the y component divided by the x component as the slope of A, right? Notice here what we have over here. This looks like, or the reciprocal of the slope, right? Specifically, the negative reciprocal of the slope. So vector B is a vector whose slope is the negative reciprocal of A. Oh Lord, what does that mean? That means that vector A is perpendicular to vector B, because two lines or vectors whose slopes are the negative reciprocal of one another give you 0, or they give you perpendicularity. But that should not be too surprising here, because if you notice, cosine of 90, right, would mean that this side of the expression would go to 0, which would mean that ax bx plus ay by, and then if we are in 3 dimensions, az bz are equal to 0. So that's really cool, because this expression then can tell me whether or not vector A is perpendicular to vector B or not, or if they kind of go in the same-ish direction or kind of go in opposite direction, which is great for comparison, especially when I've got these really confusing three-dimensional vectors that are very hard to put in your head and really hold. Now, why do I really care about that perpendicularity? Well, remember, why do we say that perpendicularity was important? We said that perpendicularity was the mathematical expression of uniqueness. Meaning here that this process can tell me if vector A and vector B are unique things, right? If they're both spatial vectors, we're going to be able to use this idea of this expression in order to come around and prove that two vectors are utterly unique from each other because they are perpendicular to each other. Awesome. So the next thing we want to do, and you might be wondering, I'm like dancing around calling this something, and there's a reason why I'm doing that. I'm going to look at the other side of the expression. Magnitude of A, magnitude of B, cosine of theta AB. So let's take two arbitrary vectors, A and B, and look at what this seems to suggest. And this is really important based on what we just talked about. Notice here, I would be multiplying together the x part of A and the x part of B, and then the y part of A, the y part of B, right? But if I just look at this side of the expression, it's kind of a little difficult to tell what's going on. But what I want to do here is I want to rotate this a little bit, because now it actually it's easier to think about, because now I've rotated this so that B is along where our x-axis was, because it's easier to think about what's going on here. And why can't I just rotate that? Well, because this product here doesn't depend upon A's relationship to the coordinate space or B's relationship to the coordinate space. These are just the magnitudes of A and B. They don't have direction. That's really good because our other half of that expression was a scalar. That means this is a scalar as well, thank God. Now, the next thing that's important is theta AB. The only thing that matters is B's relationship to A and A's relationship to B. So I can just rotate this thing, and that operation is going to come out to have the exact same value irrespective of A's and B's relationship to the axes, as long as their relationship to each other did not change. Now, if we look at this, I can use the associative property of multiplication. Let's say I talk about B parentheses A cosine theta AB. Now, if you were to look at that, that would say to multiply B times A cosine AB. Well, what is that? A cosine AB. Well, if you think about that, that is the expression that we would generally use for finding the x component of A, right? But normally, this angle here is the angle, the reference angle to the x-axis. Here it just happens to be this theta AB. So really what this is that, okay? Is that it takes this part of vector A and then multiplies it by vector B, or at least their magnitudes. Now, that's easy when thinking about vector B as the x-axis, but if I reorient it back the way it is, this is not the x component of A. This is the component of A along B, or in the language that we used recently, the projection of vector A onto vector B, right? And so what is this expression then? It's the projection of A onto B times vector B, or the magnitude of vector B. Similarly, because I said it's the associative property, I can reassociate these vectors and say A, B, cosine theta AB. And we can reimagine this not as A projected onto B, but B projected onto the line of A. and that would be vector b sub a, whereas this is vector a sub b. It's the amount of b projected on a times a. Okay, so the projection of b onto a times a. Okay, awesome. So there's a couple of different ways to think about what this process is about. Once again, why on earth are we doing this? Well, a lot of this comes down to understanding a motivation. And I want to use the work idea as our motivation of this. In class, we showed that when I lifted an object with a force upwards and it displaced upwards, that work was done. We showed that if I push in this direction and it displaces in this direction, that work was done. But when I pushed up while the object was displacing to the side, that there was no work that was done. If I'm moving forwards, but there's a force on me backwards, I'm going to slow down, right? There'd be a change in energy here, a decrease in the kinetic energy specifically. Here, in this example, if I'm moving to the right and there's a force to the right, I would speed up, right? Change in kinetic energy. Here, we have that change in potential energy going on, and we'll get into all of that. So this is a situation in which work is done. This is a situation in which work is not done. Well, how does that all relate to all of this? Notice here that work is only done when there is a component of the force along the displacement. So we need to calculate work, a mathematical operation that multiplies together the like parts of these vectors, this force vector and this displacement vector. Because you'll remember, hopefully, that the work equation was force displacement cosine theta, where theta there was the angle between the force and the displacement. Here that angle is 0, 0, 180, 90, right? Oh, 90, no work. Now notice here, this is actually a huge problem as an equation because force and displacement are both vectors, but work was a scalar. So I needed a mathematical operation that did it. Now last year we just sort of waved our hands and said, oh no, just take the magnitudes. So hopefully you're seeing now that what we've done really is we've exploited this concept here where we multiply together the like parts of the vectors, and that was the same thing as this where the force is vector A and the displacement is vector B. Okay? But more importantly here, notice what we're doing is we're multiplying two vectors together to get a scalar. So now let's abstract it out one more level. What we've been talking about since the beginning of this unit was vector addition. Vector addition was really simple. We added together like things. If vector addition exists, and we're talking about a set and groups, that there should exist vector multiplication as well. Okay? And what we've just tripped on is an expression of vector multiplication, where there is a way of talking about two things multiplied together and various things happen. So if I asked you to multiply two numbers together, say 2 and 3, there's a couple of different ways I can write that. I can write that as 2, and then we use like a dot, and then 3. Classically, you're probably taught the cross or the time, like the time signal, right? Or I could write this as 2, 3, something like that. Well, these are all the same idea if these are scalar quantities, that this comes out to be 6, that this comes out to be 6, that this comes out to be 6. But I'm going to tell you, if I'm multiplying two vectors together, 2i, 3i, 2i, 3i, 2i, 3i, these are all different processes when it comes down to talking about vectors. Okay, and so we're actually going to focus on the first of these first. This is going to be called the dot product, right? This is going to be called the cross product, and this is going to be called matrix multiplication. And the matrix multiplication is the most complex of them. It's outside of the scope of our course, but it can comprise both of these. But that's for a linear algebra course and a different day. So what we're talking about here is something that's called the dot product. The dot product was invented because there are times when we want to take something from the group of vectors or a set of vectors and come out with some sort of scalar number that describes something about that transforms this from one set into the other. And that's what this dot product is going to do. It's going to take two vectors and it's going to make a scalar. While we're at it, I will just say that the cross product, I think you can kind of see where I'm going here. This is going to take two vectors multiplied together, and this is going to give you another vector. We're not going to talk about matrix multiplication because that's, like I said, a little bit more complicated depending on what the items that you're putting into these two inputs are. But for now, we have a need for this dot product, something that takes the vectors and puts them into scalars, and there we go. So what we want to do here is define an operation. And the way we define an operation is by building up from base principles. So the dot product is called the scalar product. It is also sometimes called the inner product. We won't go into that right now. So the dot product, the scalar product, the inner product. And what this does is it takes one vector and multiplies its projection onto another vector. Okay? And that's all it does. And it acts on vectors. So what we're going to do here is we're going to define some things. So here we go. I dot I. What I dot I is really 1I dot 1I. This thing only acts on, or this operation only acts on vectors. For coefficients, which are these just scalar coefficients, it functions like normal multiplication, like it did before. And I'm then left with I dot I. So if we think about this as how much is one vector projected onto the other times the other. This is the same as that, and so when you project this onto that, you get the whole vector times the whole vector, and we're going to say that this is going to be defined as 1. So what is that? That's going to be I dot I is defined as 1. Therefore, j dot j is defined as 1. And k dot k is defined as 1. But if I take I dot j, if you think about that in the geometric interpretation, if I take I and I ask, well, how much of that is projected onto j, the answer is nothing, right? So that's going to be that. And in fact, every time that I have two unlike unit vectors that are perpendicular to each other, their dot product is equal to 0. So I'm just going to write out all of those. Did I get them all? There we go. I dot j, boom, boom. Okay, and so that's how that happens. So if I have two vectors then, vector A dot vector B, well technically that is ax I hat plus ay j hat. Actually, we'll do 3 dimensions. Az k hat dot with bx I hat plus by j hat plus bz k hat. And then I would just have to like go through all these terms. It'd be ax I hat dot bx I hat parentheses, and it would just all distribute into madness here. So ax I hat plus by j hat plus dot 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 all the way down to az k hat dotted with bz k hat, right? And there'd be 9 terms to this. But if you think about it, what's going to happen here is this term here is going to end up with being ax times bx, because they're just coefficients, times I dot I, and then this is just going to collapse to being ax bx. This term here, ax by, times ai dot j, I dot j goes to 0, so any term where the subscripts are different just fall right out of the expression, and we are left with then exactly what we came out before. So we have just a mathematical process that defines it in a way that we end up with what we said before was what we wanted. So therefore then, the dot product as a process, the dot product between two vectors is equal to the sum of the multiplications of the coefficients of the components, but it's also equal to one vector times the projection of another vector onto that vector, okay? And so those are the two definitions of the dot product. This allows us to never have to do the law of cosines again. It allows us to do all sorts of things where we have two vectors, we want to end up with a scalar. The last is this also becomes our test for uniqueness because it can figure out if those two vectors are perpendicular to each other. So in that perspective, last thing with the dot product, and then we'll be practicing it, that if I solve this for the cosine of the angle, notice that the denominator of this expression is always going to be positive, right? Remember as well that angle AB has a domain of 0 to 180 degrees inclusive, right? Because it's the angle between two vectors, folks, right? Between, so you would never go around this way. It's always this internal angle. And so the greatest that can be is 180. The smallest is 0. That tells us then, because we know cosine is positive in the first quadrant, negative in the second quadrant, that if this denominator is positive, then theta is going to be acute. If this denominator is numerator is 0, we know theta is equal to 90, as we said before. And if this numerator is equal to or is negative, then theta will be obtuse. So it's a really great way of figuring out things about the spatial relationships with two vectors. Doesn't matter how complicated those vectors are. And there you go. There's the dot product. So we want to understand it as a geometric process that relies upon projection. It is a mathematical process that takes us from vectors to scalars. It's a mathematical process that talks about how much these vectors go in the same direction. Or if you want to think of it in the most boring computational sense, there's its equation.